Section 8.2, Distribution of the Sample Proportion. Lesson objectives: describe the sampling distribution of a sample proportion. Compute probabilities of a sample proportion. Lesson objective 1. Do you strongly agree that spanking is an acceptable form of discipline? The GSS, the General Social Survey, asks this question. Do you strongly agree, disagree, or strongly disagree that it is sometimes necessary to discipline a child with a good, hard spanking? Out of 53,043 people asked, 5,264 strongly agreed. Now this is an example of a sample proportion. So if we were to take 5,264 and divide it by the total, we get 27.6%. Do you approve the way the president is handling his job? If we look at the student survey data, we see out of 543, 241 approved. So that is another example of a sample proportion. If we look at it nationally, this was a poll conducted by CNN on 5/2/2011. We see that 52% approve of Obama's performance. Margin of error, we are going to talk about that in Chapter 9 when we talk about confidence intervals. So the margin of error for this example is plus or minus 3.5%. If we were to add and subtract 3.5% from this 52%, we would have our confidence interval. But we'll talk more about that later on. Point estimate for a population proportion. Suppose that we have a random sample of size n obtained from a population in which each individual does or does not have a certain characteristic. The sample proportion, the way you read it, is p hat is given by p hat is equal to x divided by n, where x is the number of individuals in the sample with the specified characteristic. The sample proportion is a statistic that estimates the population proportion p. X would be how many people approve of Obama's handling of his job, and n would be the number of people asked. Let's look at an example. In a survey of 1,000 U.S. adults, 662 said it is acceptable to check personal email while at work. Find the point estimate for the population proportion of U.S. adults who say it is acceptable to check personal email while at work. In this case, we see the n is 1,000. X is how many people say it's okay, which is 662. So p hat is 662 divided by 1,000, which is 0.662, or approximately 66.2%. Are you in favor of the death penalty for a person who is convicted of murder? This time series graph shows from the Gallup poll the percentage of people who are in favor and the percentage who disapprove of the death penalty for a person convicted of murder. And if we look at the details, we would see the results are based upon telephone interviews with 1,013 national adults aged 18 or over, and this was conducted on October 1st through the 4th, 2009. So the results are based upon a total sample of national adults. One can say with 95% confidence that the maximum margin of error is plus or minus 4 percentage points. Again, this is reference to a confidence interval, which we'll learn in Chapter 9. So here's some key points about the distribution of sample proportion. As the sample size n increases, the shape of the sampling distribution of the sample proportion becomes approximately normal. The center, the mean of the sampling distribution of the sample proportion, equals the population proportion, p. And the spread, the standard deviation of the sampling distribution of the sample proportion, decreases as the sample size n increases. For a simple random size n for a population proportion p, the shape of the sampling distribution of p hat is normal provided that n times p times 1 minus p is greater than or equal to 10. So this is a requirement here for it to be normal. The mean of the sampling distribution of p hat is the average of all the p hats will equal the population proportion p. And the standard deviation of the sampling distribution of p hat is given by this formula, the square root of p times 1 minus p divided by n. The model on the previous slide requires that the sampling values are independent. When sampling from finite populations, this assumption is verified by checking that the sample size, n, is no more than 5% of the population size. Regardless of whether n times p times 1 minus p is greater than or equal to 10 or not, the mean of the sampling distribution of p hat is p, and the standard deviation is the square root of p times 1 minus p divided by n. Lesson Objective 2. If you recall, our z-score is our x minus the mean divided by standard deviation. So if we're looking for a z-score for p hat, we take our p hat minus the mean of the sampling distribution of p hat divided by the standard deviation of the sampling distribution of p hat. Let's do an example. According to the Centers for Disease Control and Prevention, 18.8% of school-aged children aged 6 through 11 years are overweight in 2004. A. In a random sample of 90 school-aged children aged 6 through 11, what is the probability that at least 19 are overweight? We first have to check our requirements. 90 is less than 5% of the population size for school-aged children aged 6 through 11. So that's a check. N times p times 1 minus p would be our sample size, 90, times p times 1 minus 0.88 yields 13.7, which is greater than or equal to 10. So that's a check. So our requirements have been satisfied. So that means the distribution of p hats is approximately normal with a mean of 0.188 and a standard deviation equal to 0.0412. So in order to answer the question, we first want to find our z-score. So we take our p hat, 0.19, we subtract our mean, 0.188, and we divide it by our standard deviation, 0.0412. So our z-score is approximately 0.05. Looking at the picture, our z-score of 0.05, we want the probability of at least, and at least means greater than. So using table 5, the probability of z being greater than 0.05 is 1 minus what's in the table, 0.5199, which gives us a probability of 0.4801. Let's look at B. Suppose a random sample of 90 school-aged children aged 6 through 11 resulted in 24 overweight children. What might you conclude? We compute our p hat, x over n, which is 0.2667. We change that to a z-score. We take 0.2667 minus the mean, 0.188, and divide it by the standard deviation. We get a z-score of 1.91. So if we draw a picture, 1.91, we want greater than. Using table 5, the probability that z is greater than 1.91 is 1 minus what's in the table, 0.9719, which is equal to 0.028. What might we conclude? We would only expect to see about 3 samples in 100, resulting in a sample proportion of 0.2667 or more. This is an unusual sample if the true population proportion is 0.188. So it could be that the actual population proportion is higher than this. Here's the readings and suggested problems. Thanks for watching.